This lecture covers Chapter 5, specifically sections 5.1 through 5.4, and also section 5.6. First, let's talk about propositions. A proposition is a statement that can be either true or false. In logic, we represent propositions symbolically so that a computer can reason about them in a structured way. A proposition might represent something simple, such as an admin login occurred, or a large data transfer happened. The important idea is that propositions give us a precise language for describing events. Once events are represented as propositions, we can begin to reason about them systematically rather than relying on intuition or informal judgment. And this slide shows some of the formal notation of propositional calculus syntax. Propositional logic is built from atomic propositions and logical connectives. An atomic proposition is a simple statement like failed login or external IP access. We then combine these atoms using logical operators such as and, or, not, and implication. These operators allow us to construct structured rules. For example, we might say that an account compromise occurs if there are multiple failed logins and an unusual login time. This syntax is the foundation for rule-based detection systems in cybersecurity. So why do we use propositional logic instead of just storing raw data? Because logical formulas are modular and easier to analyze. They allow us to express what is known to be true in a structured way. Logical rules are easier to check, debug, and extend than large tables of possible situations. Most importantly, logical representation supports explanation. If an alert is triggered, the system can show which conditions led to that alert. That traceability is what makes rule-based systems inherently explainable. Detection systems do not directly observe attacks. They observe signals and they infer conclusions. For example, suspicious login behavior combined with privilege escalation might lead to the conclusion that an account is compromised. Logic provides the structure for making that inference. It tells us exactly which conditions must be satisfied for an alert to occur. Without logic, detection is simply correlation between events. With logic, detection becomes structured reasoning that can be audited and explained. And this slide shows the semantics of the propositional calculus. Semantics refers to meaning, specifically how we determine whether a logical statement is true or false. An interpretation assigns true or false values to each atomic proposition. Once we know the truth values of the components, we can determine the truth of compound statements using rules like those shown in the truth table. This matters because cybersecurity systems operate over many possible combinations of events. Logical semantics allows us to evaluate these combinations consistently and determine what conclusions follow in each possible case. A model is a possible world in which all of the statements in our knowledge base are true. When we say that a conclusion is a logical consequence of a knowledge base, we mean that it must be true in every possible model where the knowledge base is true. In other words, there is no possible situation in which the rules are true and the conclusion is false. This is powerful in cybersecurity reasoning. If an alert logically follows from observed facts and rules, then the system is justified in raising that alert. From a human perspective, we start with a real-world domain, such as login behavior or network activity. We then choose propositions that represent meaningful events in that domain. After encoding knowledge as logical rules, we ask the system questions. The system tells us whether a conclusion logically follows. Importantly, humans provide the meaning. We interpret what account compromise or data exfiltration actually represents. The logic engine simply evaluates the structure. But from the computer's perspective, on the other hand, there is no understanding of meaning at all. The system only sees symbols and rules. It does not know what an admin login is. It only knows whether certain conditions are true and whether certain conclusions follow. This distinction is important because it explains both the power and limitations of rule-based systems. They are precise and consistent, but they only reason within the structure we provide. So to make reasoning efficient, we restrict ourselves to a simplified form of logic called definite clauses. A definite clause is either a fact or a rule written as head if body. This structure mirrors how many detection systems are implemented. For example, we might write, account compromise occurs if there are multiple failed logins and an unusual login time. By restricting the language, we make inference more efficient and easier to manage in real-world systems. So now let's look at a concrete cybersecurity example. Suppose we define a rule that account compromise occurs if there are failed admin logins and a login from a new country. And then we define another rule that data exfiltration occurs if there is an account compromise and an unusually large outbound transfer. Now assume the system observes failed admin logins, a login from a new country, and a large outbound transfer. Using forward reasoning, the system first derives account compromise. Then it derives data exfiltration. And this is exactly how rule-based detection systems escalate alerts in practice. Now, a proof is a mechanical demonstration that a conclusion follows from a knowledge base. So when you write the symbol that you see in the second bullet here, it means that G can be derived from knowledge base KB using a proof procedure. And then when we write that symbol that you see in the third bullet point, that one means that G must be true in every model of the knowledge base. So in well-designed systems, our proof procedures are sound, meaning they only derive correct conclusions. And the takeaway from this is that a rule-based detection system is not guessing. It is deriving conclusions according to defined logical rules. So now let's apply logical consequences to a cybersecurity example. Suppose our knowledge base contains two rules. Privilege escalation occurs if there is an admin login and an unusual IP address. And data exfiltration occurs if there is a privilege escalation and a large data transfer. Now assume the system observes an admin login, an unusual IP, and a large transfer. Because those conditions satisfy the rules, the system can derive data exfiltration. It did not match a pattern randomly. It followed the structure of the rules. So this is logical consequence in action. Now, the bottom-up proof procedure works by starting from known facts and applying rules forward. If the body of a rule is satisfied, then the head of the rule becomes true. This is sometimes called forward chaining. In cybersecurity systems, this mirrors how alerts escalate. If events are observed, the system checks which rules apply and derives higher-level conclusions automatically. And the bottom-up algorithm shown in pseudocode here repeatedly adds new conclusions as long as new rules can be satisfied. We start with an empty set of derived facts, then we add any facts that are directly observed. After that, we check which rules can fire. When no new conclusions can be added, the process stops. At that point, the system has reached a stable belief state. This is how rule-based detection systems build up their understanding of what is happening. The set of conclusions reached at the end of forward reasoning is called a fixed point. It is fixed because no additional rules can fire. In practical terms, this represents the system's final belief state given the observed events. If a conclusion can be logically derived, it will appear in that final set. This concept helps explain why rule-based systems are deterministic. Given the same inputs and rules, they will always reach the same fixed point. In a real security operations center, logs arrive continuously. Facts accumulate. As soon as enough conditions are satisfied, rules fire and higher level alerts are generated. The system keeps applying rules until no new alerts can be derived. That stable set of alerts is the fixed point. This process is exactly what we mean by escalation logic. It is structured, repeatable, and explainable because each alert can be traced back to the conditions that caused it. So far, we have looked at forward reasoning, where we start from facts and move upward to conclusions. Now we consider top-down reasoning. In top-down reasoning, we begin with a query, something we want to know, and we work backwards to determine whether it can be supported by the knowledge base. Instead of asking, what follows from these facts, we ask, what must be true for this conclusion to hold? This approach mirrors investigative reasoning. The top-down interpreter formalizes that backward reasoning. We begin with a query and repeatedly replace it with the conditions that would make it true. If those conditions are satisfied by known facts, the query succeeds. If they cannot be satisfied, the query fails. In practical cybersecurity terms, this resembles asking what evidence would support the conclusion that data exfiltration occurred, and then checking whether that evidence exists. In real-world incident response, analysts rarely start from raw logs and move upward. Instead, they begin with a hypothesis. For example, they might ask, did data exfiltration occur? Then they look for supporting evidence. Was there privilege escalation? Was there an unusual transfer? Backward chaining is structured suspicion. It formalizes how investigation proceeds from a possible conclusion back to the required evidence. One of the strengths of rule-based systems is that they can explain their reasoning. A user can ask, how was this alert derived? And the system can point to the specific rule and conditions that led to it. Users can also ask, why did you ask for this information? And the system can explain which higher-level rule required that condition. This kind of traceability is what makes rule-based AI inherently explainable. Analysts cannot always anticipate which pieces of evidence matter. They may not know which rule is currently firing or which assumption triggered escalation. The system must therefore expose its reasoning. It must show which premises were satisfied and how they led to the alert. Explainability is not an optional feature. It is the difference between trusting a system and blindly accepting its output. In cybersecurity, that transparency is essential. Now, not all facts in a detection system come from logs. Some facts require human confirmation. For example, an unusual login might be legitimate if the user is traveling. A large transfer might be authorized if it is part of a scheduled backup. In rule-based systems, we can think of three kinds of propositions: observed facts from sensors, derived conclusions from rules, and askable facts that require human input. A transparent system distinguishes among these categories so that analysts understand what is inferred and what must be confirmed through human input and asking questions. Even well-designed rule-based systems can make mistakes. There are several types of logical errors that can occur. The system might derive an incorrect answer, fail to derive a correct answer, enter an infinite reasoning loop, or ask irrelevant questions. These are not random failures. They reflect flaws in the rule structure or missing conditions. Debugging a rule-based system, therefore, means analyzing its logic, not just adjusting thresholds. A false positive occurs when the system derives a conclusion that is not actually true in the real world. Logically, this means a rule fired even though one of its premises should not have been satisfied. The error could come from a condition that is too broad or from an incorrect assumption encoded in the rule. To debug a false positive, we examine which rule triggered and which premises were considered true. This process is systematic and explainable because the reasoning path is visible. And it's important to understand that false positives are not just operational annoyances, they are logical failures. A premise may have been modeled incorrectly, or a necessary condition may have been omitted. In rule-based systems, detection tuning is really model repair. We refine the structure of the rules so that conclusions better reflect reality. This reinforces the importance of careful rule design. A false negative occurs when a serious event happens but no alert is generated. Logically, this means the necessary rule did not fire. Either the system lacks an appropriate rule or one of the required premises was not represented correctly. False negatives are often more dangerous than false positives because they create a false sense of security. Just like false positives, false negatives reflect gaps in the logical model and must be addressed by revising the rules. So far, we have looked at rules that derive conclusions. Integrity constraints work differently. Instead of deriving a new alert, they declare that certain combinations of conditions are impossible or unacceptable. An integrity constraint has the form false if these conditions occur together. This allows the system to detect contradictions. In cybersecurity terms, integrity constraints represent policy violations or states that should never occur. Horn clauses include both definite clauses and integrity constraints. A definite clause derives something when conditions are met. An integrity constraint declares that something is inconsistent when certain conditions occur together. Horn clauses are important because they allow efficient reasoning while still being expressive enough for many real-world detection and policy systems. Many rule-based security tools operate using structures very similar to horn clauses. Security policy can be viewed as logic that forbids certain possible worlds. For example, an admin login from an external IP without multi-factor authentication may be unacceptable. In logical form, we write that as a rule implying false. If those conditions are all true, the system recognizes a violation. Policy is not just advice. It eliminates entire combinations of states from being considered valid. This is how logical systems enforce constraints. Logical systems can also derive negative conclusions. If certain combinations of facts would lead to a contradiction, the system can infer that some other condition must be false. This kind of reasoning is important in diagnosis. Sometimes we do not directly observe a failure. Instead, we infer that something must not be true because otherwise the system would be inconsistent. Logical reasoning allows us to derive those negative conclusions in a structured way. In Horn knowledge bases, some propositions are considered assumable. These are statements we are willing to tentatively accept in order to explain observations. A conflict occurs when a set of assumables together implies false. A minimal conflict is the smallest such set. This concept is central to diagnosis. If a combination of assumptions leads to inconsistency, at least one of them must be wrong. Logical diagnosis works by identifying which assumptions must be rejected. A consistency-based diagnosis is a set of assumptions that explains the observed inconsistency. If certain combinations of conditions cannot all be true at the same time, then at least one of the underlying assumptions must be false. A minimal diagnosis is the smallest set of assumptions that resolves the conflict. In cybersecurity, this mirrors root cause analysis. When a system behaves inconsistently, we search for the smallest explanation that accounts for the problem. Diagnosis is not guessing, it is structured elimination. If we observe something like data exfiltration while other components appear normal, then some assumption in our model must be wrong. Logical diagnosis systematically identifies which assumptions could be false. Instead of randomly speculating, we narrow down possibilities using the structure of the rules. This makes investigation disciplined rather than intuitive. Assumption-based reasoning allows symptoms to make temporary hypotheses. In abduction, we assume possible causes to explain observations. In default reasoning, we assume normal conditions unless there is evidence otherwise. In cybersecurity, this is common. We may assume a system is functioning normally until logs suggest compromise. These assumptions allow the system to function efficiently without requiring complete certainty at every step. And there are two major uses of assumption-based reasoning: design and recognition. In design tasks, such as building a plan, we can choose among multiple valid solutions. In recognition tasks, such as identifying an attack, we cannot choose the explanation we prefer. We must determine which one is actually true. In cybersecurity, most diagnostic tasks are recognition problems. The system must determine what happened, not what would be convenient. Default reasoning is used when the truth of something is unknown, and we tentatively assume normal behavior. Abduction, on the other hand, begins with an observation and searches for explanations. In cybersecurity, threat hunting often relies on abduction. We observe unusual behavior and we ask what could explain it. Then we use default reasoning to extend those hypotheses and determine what other consequences would follow if they were true. Threat hunting is a practical example of abduction. We begin with an observation such as unusual DNS activity and then ask what could explain it. Possible explanations might include a compromised host, malware beaconing, or even misconfiguration. Abduction generates candidate explanations. From there, we use additional evidence and reasoning to narrow down which explanation is most plausible. This is structured hypothesis generation rather than random guesswork. In logical systems, we distinguish between primitive and derived atoms. Primitive atoms represent directly observed facts, such as a login event or a file transfer. Derived atoms represent conclusions inferred from rules, such as account compromise or data exfiltration. This distinction matters because derived conclusions depend on the structure of the rules. If primitive facts change, derived conclusions may also change. So now consider how primitive and derived atoms interact. If one proposition depends on another through a rule, then changing the truth of the primitive atom may change the derived atom as well. This highlights an important modeling principle. Dependencies matter. In cybersecurity detection, a high-level alert depends on lower-level conditions. If those lower-level signals are inaccurate, the derived conclusions will also be inaccurate. A causal model goes beyond correlation. It represents how interventions change the world. An intervention forces a variable to take a specific value. For example, disabling an account is an intervention. A structural causal model defines how each proposition depends on others. If we manipulate one part of the system, we can predict how other parts will change. This is critical for automated response systems. Evidence and cause are not the same. An evidential model may show that two events are correlated, but a causal model explains what would happen if we intervene. In cybersecurity, automated response requires causal reasoning. If we disable credentials, isolate a host, or revoke privileges, we are changing the system. To do that safely, we must understand cause and effect relationships, not just correlations. And some logical relationships are symmetric in purely evidential terms, meaning they describe correlation without direction. But causal reasoning is asymmetric. Changing one variable may affect another, but not vice versa. This distinction is important. Just because two events occur together does not mean they influence each other equally. In security systems, we must be careful not to confuse correlation with causation. And finally, a structural causal model can be expressed using logic rules. However, not every logical model captures causality correctly. An evidential model may answer questions about what is likely true, but it may fail to predict what happens when we intervene. For automated cybersecurity response, understanding interventions is essential. We must know not only what follows from evidence, but also what will change if we act.